So, hello everyone. I am Shakshi Panwar and this is my teammate Mahi Jindal. So, together we are going to present our project on LLM model quantization. So, the LLM, like we are first, we are see the LLM comparison. So, LLM comparisons, so sorry. LLM compression refer to the techniques used to reduce size and computational requirement of a large neural network model, so while maintaining acceptable performance. So one of the important approach for LLM compression is LLM model quantization. So LLM model quantization, a technique that is rapidly become the one of the most important tools in making AI accessible and deployable in the world. So let's start. So before the like we drive before we drive deep, let me give you a quick overview of what we will cover today. So we will begin with what quantization is, and then move to why it is needed, and we will explore the different quantization technique, benefits, and finally look at how it applies to LLM models through our actual projects. So, what is the motivation? So, motivation, like what, why does quantization matter? So, AI, we all see modern AI model, especially LLM models, are extremely large. So, they contain billion of parameters and demand huge memory, and they are computationally expensive. So, so now the solution is model quantization. So, what is quantization? Now, quantization is the process of reducing the precision of numerical value, especially weights, and used inside a neural network. So, let's look at the image on the right. So in this on the left image, original of cookies, like highly detailed, rich in color, and after the quantization image we can see its look slightly different with favored distant color value shown at the bottom. So you can still clearly recognize it is a cookies. So this is exactly what quantization does to a model. It reduces the details slightly, but the model still work well. So in technical terms, we use FP32 for 32 bits per value, and FP16 equal to 16 bits, half the size, and int8 equal to 8 bits, one quarter of FP32, and int4 is 4 bit, one eighth of FP32. So the core idea is lower precision equal to smaller model size. So why quantization is important? So it's perfectly summarized the like five key benefits, like reduce model size, less storage needed, faster inference speed, quick response, and lower hardware requirement, so no need for expensive GPUs, and lower power consumption, so it's cheaper to run, and enables deploy to edge device like smartphones, IoT device, and other. So end of the bottom of the image shown the number clearly. 8-bit quantization equal to 50% memory reduction, you cut memory in half. 4-bit quantization equal to 75 memory reduction, three quarter of memory saved. So these are not small improvements. So these are kind of gains that make the difference between being able to deploy a model or not. So type of quantization. So these are four quantization approach in this diagram. Three top level category like PTQ, post training quantization, QAT, quantization aware techniques, and uh, dynamic quantization and static quantization. So what is like post training quantization, PTQ? So the first one most widely used method is PTQ. So in the diagram, you we can see we can start with a pre-trained full precision model, and after that evaluate it with calibration data, and run it through a quantization algorithm, and after the result is quantize int 8 model smaller and faster. Though, so the steps are simple. First, the train the model normally in full precision, and after that, convert the weight to lower precision using the quantization algorithm. After that, deploy the comparison model. So the advantage is simply to apply, no retraining needed. And next one is QAT. So QAT is quantization average technique. So in the diagram, uh, unlike PTQ, in QAT you take the full precision model and then do training with quantization simulation. Like the model learns during training what is will be quantized or not. So it adapts. So the result is still quantized int 8 model, but the time the model has been specially handled to train to it. And the advantage is higher accuracy than PTQ. So PTQ is like putting someone in a cold room suddenly, while QAT is the like gradually training them to handle cold weather. So QAT model is better prepared. So next one is static quantization. So static quantization is both weight and activation. So convert the both weight and activation before inference even begun. So the process is done. First run calibration using a small representative data set. After that, use the calibration data to determine fixed quantization parameters. And after that, convert the entire model with those parameters. So the better overview overall performance than dynamic quantized because everything is pre-compute and fixed. And next one is dynamic quantization. So the diagram are here. So static versus dynamic quantization. So static quantization use calibration data, fixed quantization range, and you quantize once, then apply. But in the dynamic quantization, need no calibration. It adapts range dynamically and quantize on the fly during inference. So a dynamic quantization feature is like only weights are quantized and activation remain in high precision at the runtime. So the advantage is easy to implement and good for CPU inference. And next one is quantization technique. So now let's talk about the actual tools and techniques used in practice. Like three popular ones. First in bits and bytes, it's a very efficient loading of large models, and it supports both 8-bit and 4-bit. So and GPTQ is generative pre-trained transfer quantization, a powerful post-training quantization method highly optimized for transfer-based model like GPT. So GSQ is group scale quantization, a never technique that apply quantization at the group level for a better accuracy. But in our project, we are using bits and bytes. Now, Mahi can take over here. So, the project introduction.
Hello, good morning, everyone. My name is Mahi. Let's talk about benchmarking quantized language models for efficient inference. The core goal of this project is to evaluate how model quantization affects three key aspects: model size, language model quality, and inference speed. To do this, we tested three configurations: FP16 baseline, 8-bit quantized, and 4-bit quantized. The model we worked with is OPT 1.3b, and we evaluated it on the Wikitext 2 dataset. Let's dive into the next slide. So here are project objectives. We had four main objectives. First, to compare different quantization levels. Second, to measure how much efficiency improves with compression. Third, to evaluate the impact quantization has on language modeling quantity. And fourth, to analyze inference performance across configurations. To capture all of this, we tracked four matrices throughout the experiment: model memory size, perplexity, latency, and throughput. These four tell you about the how model behaves under different precision settings. Now let's talk about system architecture. The workflow follows six clear steps. We can start by loading the data set, then load the tokenizer, followed by the baseline model. And from there, we apply quantization, measure the performance matrix, and finally compare the results across configurations. This end-to-end pipeline ensures everything is systematic and reproducible. So here's a visual representation of the TAT pipeline. Data flows from the dataset into the tokenizer and then into the model. From there, we branch into quantization. Either it would be a 8-bit or 4-bit, followed by benchmark evaluation, and finally we arrive at the results. Every step feeds cleanly into the next, which is what makes the comparison valid and fair. Now, to run this experiment, we relied on four core libraries. PyTorch handles all the deep learning computations. Transformers from Hugging Face is what we use to load pre-trained models. The dataset library let us pull in our benchmark dataset with ease. And Bits and Bytes is a key library that actually performs the model quantization. Together, these four tools form the complete technical foundation of the project. Oh, 1 second. So here you can see as a code package, which first it describes how what we install in the what we install package libraries talk vision, talk audio, and after that we firstly clear GPU cache and then load small portion of Wikitext test set, and then we have used the model Facebook OPT 1.3b. As you can see, we have load tokenizer and model in FP16 as a baseline. So for evaluation, we used Wikitext 2 as a standard, which is widely used benchmark in a language model research. It is particularly well suited for measuring perplexity, which is one of our key metrics. The dataset consists of English Wikipedia articles, making it clean, natural language text that is representative of real-world usage. It is widespread adoption in the research community also means our results are directly compared to other published work. And model we choose for this experiment is OPD 1.3b, as you know. So it has 1.3 billion parameters and uses a standard transformer based architecture. It's a fully open source, which makes it accessible and transparent. Most importantly, it's well suited for research benchmarking, large enough to be meaningful, but manageable enough to run quantization experiments on without needing massive infrastructure. Now, let's start with the baseline model. The first step in our experiment was to load the model in FP16 precision. That's the 18-bit floating point. As you can see here, this part. The purpose here was simple: establish a reference point. Before we apply any compression, we need to know what normal looks like. We measured four things: model size, perplexity, latency, and throughput. Every technique we test after this will be compared against these numbers. Next is 8-bit quantization. Using the bits and bytes library, we configured it with load in bit 8-bit equal true and set the compute t-type to float 16. What does this actually buy us? Roughly a 50% reduction in memory usage with minimal accuracy loss and faster inference. That's a compelling trade-off, and you are cutting your memory footprint in half. Now we push further with 8-bit, 4-bit quantization. The configuration mirrors the 8-bit setup but with low 4-bit equal to true. The benefits are even more dramatic. A very small memory footprint, faster inference, and suitability for low memory GPUs. And but a slight decrease in model accuracy. Now, to evaluate all of this efficiently, we use a single unified function called combined benchmark. Rather than running separate tests for each metric, this function captures everything in one pass, which is model size, average perplexity, average latency, and token throughput. This ensures a fair, consistent comparison across all three model configurations. Now, experimental comparison, here's where it all comes together. The FP16 baseline has the largest model size, stable perplexity, and metric speed. 8-bit quantization gives us a small model with only a slight change in perplexity and a model speed improvement. 4-bit quantization delivers the smallest model size with minimal impact on performance and the best efficiency. So here we can see that quantization dramatically reduces memory requirements while keeping performance largely intact. So we have here we have done of a baseline that is FP16, and here we done of 8-bit quantization with this combined benchmark. First was by loading 8-bit and second by bits and bytes configuration in the 8-bit only. And last we have done with the 4-bit, which is done by bits and bytes. Now I give it to Ms. Shakshi for the presentation.
So now we see the graph graphically, what the size comparison and perplexity comparison and latency or throughput. So first we see the this graph. This is the size graph basically. So in a blue bar we can see PF16, PF16. This is the value is 2700 of 2700 05.998 MB. so the largest number. And after the using 8 bit orange bar, so the size is 1553.98 MB. So a reduction of about 848 MB, like then is 31% smaller. And then after the we can see the green bar, it's we are using in 4 bit, so the size is 977.98 MB. So the smallest and roughly 64% smaller than PF. So you can easily see how dramatically the model sync with each level of quantization, going through like 2.7 GB to under 1 GB is a massive practical improvement for deployment. After moving the second graph, perplexity comparison. So now see the uh, lower is better because it means the model predicts a language more accurately. So Mahi, please move next slide. So we can see in this graph perplexity. So yes, so we can see first PF16 equal to 100 is 2.65 our baseline, and after that 8 use 8 bit, it's going to 100.41, almost identical, only 2.24 point lower, practically no quality loss. And after we use 4 bit, it's going to 84.22, actually the best perplexity of all three. So this is the very interesting finding. The 4-bit model perform better than the baseline on this matrix. So this can happen because quantization in some case act like regularization, helping the model generalize better on the particular data set. So the key takeaway is quantization does not hurt quality. It's our experiment is actually helped. So next slide, it's latency comparison. So in latency, we can see FP16 blue is to 2654.98 ms, our baseline, fastest standard performance. But after we use 8 bit, it's going to 15,083.05 ms, actually higher, much higher. But why? After we use 4 bit, it's green, it's 3850.7 ms, lower than 8 bit but slightly higher than FP16. So the 8 bit latency is high because bits and bytes perform dequantization on the fly during computation, which introduce overhead especially on CPU. And the 4-bit model use a more optimized execution path, which is why is the faster than 8-bit. This is so that quantization level and latency don't always follow a simple linear pattern. It's depend heavily on the hardware and the library optimization. So the next slide, we are talking about throughput comparison. So in this throughput graph, so throughput is token per second. Like FP16 is 52.02 token per second, nearly flat on this graph. And we talk about 8 bit. So 8 bit is 8.71 token per second, lower due to dequantization overhead. But in but in 4 bit, it's 3850.7 token per second, a absolutely massive spike. So the 4-bit model generates nearly 4,000 token per second, then is 74 times faster than FP16 in throughput. So this is a dramatical result comes from the 4-bit model highly optimized kernel in bits and bytes, which is specially trained for 4-bit matrix multiplication. So the demonstrate the transformative potential of aggregation quantization when the right optimization are in place. So next the conclusion. So let's bring it all together. So our experiment with OPT 1.3 B billion model and Wikitext 2 proved 5 key things. First, quantization significantly reduced memory. So we went from 2705 MB down to 977 MB. It's a 64% reduction with 4 bit. And the second is language quality is preserved. So the 4-bit perplexity of 84.22 was actually better than FP 16 baseline of 102.65. And third is latency. So latency result depend on hardware optimization. Uh, so the 8-bit model so higher latency due to dequantization overhead, while 4-bit recovered well. And fourth is throughput. So throughput can be dramatically improved when we use 4-bit delivery nearly 3800 51 token per second compared to just 52 for FP16. So next one is our experiment was fully implemented, debugged and validated on Google Colab. So and the notebook is publicly available now. We are working on it. And the conclusion is clear. 4-bit quantization provide the best overall efficiency with acceptable and even improved performance trade-off. So thank you. Thank you all.
Yeah, thank you, Saxi, Mahi. So if you have any questions, feel free to ask.
Yeah. So thank you for presenting. It was wonderful presentation. I have two things in my mind which I would like to ask. So what do you mean by accuracy loss? Like specifically, when we reduce from FP30 to FP16, like what is the loss actually we're facing? Like, is the model is less knowledgeable? Like we mentioned that with slightly accuracy loss. So what is the accuracy loss? Could you please tell?
So
Mm-hmm.
accuracy like loss from